We'll continue with another try in first order kinetics. Top of page 8 in our notes reads, the decomposition of dimethyl ether, which has a formula CH3 taken twice O at 510 Celsius, is a first order process. It also tells us the rate constant, 6.8 times 10 to the negative fourth per second. I did not mean to superscript the time. That was an error. So let's see what we have. First order tells us, turn your attention to the first order kinetics right here. The rate constant is given as 6.8 times 10 to the negative fourth. That should be superscript. This should be seconds to the negative 1. Since it's a gaseous reaction, it's going to talk about pressure given in torr. Instead of molarity units, we will now use torr for pressure. So our first order reaction would look like the natural log, and we use the partial pressure of our reactant, CH3 taken twice to O, at any point in time. P, of course, is partial pressure. I'm just putting parentheses around that, is negative KT plus the natural log of the partial pressure of our reactant, CH3 taken twice O, and I'll close the parenthesis and put a 0 to say the original amount of pressure. No difference in the math. I'm just showing partial pressure instead of big M molarity units. If the initial pressure is 135 torr, that's this guy at the end. What's the partial pressure after 1420 seconds? I check to see if my rate constant matches the time unit. It does indeed. It's in a per second. The natural log of our reactant, I'll just switch to A at any time t, is equal to negative K given to us, 6.8 times 10 to the negative fourth per seconds, times the amount of time that went by, 1420 seconds, plus the natural log of the original pressure given to us is 135 torr. We want to know the partial pressure of our reactant after 1420 seconds have gone by. When I simplify by hitting the right-hand side, let's do that together on our calculator. Negative 6.8, second function E negative 4, times 1420 equals, right now I'm at negative 0.9656, plus, parenthesis, natural log of 135, close parenthesis, twice. Right now, I have a value of the right-hand side simplified as 3.94. We want to know the partial pressure of our reactant without the natural log in front of it. So that's our E raised to the 3.94. So on our calculator, partial pressure of A, I hit second function, ln. Now my screen is saying E caret key. And I'll press in 3.94, close parenthesis, and my answer, 51.4 torr. Oftentimes we talk half-life. Half-life is particularly important when we think about radioactive decay. How much time does it take for the original amount of reactant to reach half of that amount? So the time required to reach half of the original concentration, I'll write that as the original concentration at time 0. That's what we're measuring with a half-life, the time required to go half as much. In the first order reaction, just to share, this is on our screen here as well. The half-life for first order reaction is the natural log of 2 over K. And just to share that development is a little bit of math here. When the concentration of A equals the original amount divided in half, when time is exactly 1/2. That's what we're looking for. And simplifying that integrated rate law, the natural log of 2 is equal to k times the half-life. So what we're looking at really is just simplifying the natural log of 2. Test it on your calculator. If you hit natural log of 2, it reads 0.693147. I sometimes think it's easier to memorize natural log of 2 instead of 0.693, but whatever you find to be most easiest. The half-life in a first-order reaction is the natural log of 2 set over k, where k is the rate constant given to us typically in the formula. So the time to reach half the original concentration does not depend on the starting concentration. It will in second-order reactions, but it does not for first order. In other words, the natural log of 2 is equal to k times our half-life, half the time that went by. This is often an easy way to solve for k, the rate constant. If you know the half-life, you can solve for k. If you know k, you can solve for the half-life simply by looking at that relationship where the half-life is equal to the natural log of 2 over k, which is the same as 0.693 over k. Whatever you find easiest, perhaps you like either one. So a first-order half-life does not depend on the starting concentration. And it remains constant throughout the entire reaction. It will be different for a second-order reaction. So the concentration of the reactant decreases by 1/2 in each of a series of regularly spaced time intervals, namely T1/2. Radioactive decay is a prime example in a nuclear reaction. The more stable an isotope, the longer its half-life. The quicker the half-life, the more unstable that radioactive decay. So let's do a little practice here. Practice with the half-life reads, the decomposition of N2O5 into 2 units of NO2 and half O2 in a carbon tetrachloride solvent is first order with a rate constant of 6.2 times 10 to the negative 4th per minute at any given temperature. What is its half-life? Half-life is equal to the natural log of 2 set over k. We are solving for the half-life given the k constant. So the natural log of 2 simply set over 6.2 times 10 to the negative 4th per minute. And if we hit that on our calculator, natural log of 2 divided by 6.2 e negative 4 . My calculator is reading, and it's pausing for effect.